Okay, so for today's lesson, this is topic 16.4. This is the last topic of chapter 16, and we're doing nuclear fission and nuclear fusion. Okay, so we're going to start off with fission. So nuclear fission, this is the process by which a nucleus with a atomic number greater than 120 will split into smaller nuclei. Okay, so remember atomic number. There we go. Atomic number tells us the number of protons present. Okay, so if a nucleus has more than 120 protons, it will split into smaller nuclei. Okay, so just like we have here, we have a large atom here, and it is splitting into two smaller nuclei, and energy is going to be released. Okay, so energy is released as a byproduct of fission. All right. So why do we have release in energy here? Well, remember from topic 16.1, we learned about the binding energy of nuclei, and we wanted to find the binding energy per nucleon. We would divide that by the atomic number, right? And to find that, it was the energy of the nucleons subtract the energy of the nucleus, right? And we found that the higher binding energy per proton, we looked at that graph, right? We found that iron was the most stable element, and that was because of the ratio between the protons, neutrons, the nucleons in there, right? Because iron, it is the most stable nucleus due to the attractive force between nucleons, so protons and neutrons. And iron 56 has the lowest average mass per nucleon. Okay, so it's quite stable. Now, when we have an unstable large atom, it will decay into two smaller nuclei and release energy. So that is nuclear fission. Okay, in this case, for fission, just one note here. So the nucleus, the parent nucleus is losing mass. So giving off energy. Okay, so that is fission. And it's giving off energy. Remember from Einstein, we know that the change in energy is equal to the change in mass times the speed of light squared. Okay, so we're going to use that formula again today. All right, so the year is 1939, and Lise Meitner, I don't know the pronunciation for that, I apologize. But anyway, so she and her nephew observed uranium exploding into two smaller nuclei. And this process released energy, and more energy was released than when atomic or radioactive nuclei would decay through transmutations, right? Remember, transmutations is when parent nuclei decays into a daughter nuclei, which may be radioactive. Okay, so Meitner found that when an atom or a nucleus split into smaller nuclei, more energy was released, and Meitner called the process nuclear fission. Okay. 3 years later, Enrico Fermi comes along, and he is able to conduct the first controlled nuclear fission chain reaction. Okay, so he does this under a particular set of temperature and pressure, and he's able to kind of he controlled this chain reaction, so he's able to kind of acquire the energy release during the fission. Okay, so as that uranium-235 continues to decay by neutron decay, and it will release energy. Okay, in 1945, so 3 years later from there, and so this is just 6 years after nuclear fission was first termed, the first uncontrolled nuclear reaction took place, and this was the first detonation or the first testing of the atomic bomb. Robert Oppenheimer, he was the physicist that was kind of spearheading the Manhattan Project, and the Manhattan Project is just the development of the nuclear bomb. Okay, this development, the Manhattan Project, is actually a pretty interesting story. Once Oppenheimer had seen the destruction of his bombs, he has gone on to be quoted, and he said, quote, "I have become death, destroyer of worlds." It's pretty scary quote. And yeah, again, this was once he saw the damage that was caused by the explosion of his bombs, which he helped develop. Okay, there is a good video on the Manhattan Project. I have included this link in the chapter 16 video link document, so please take the time to watch this video today, please. Okay, so let's get into a nuclear fission example. So we're to write the nuclear equation and calculate the energy released with when uranium-235, so 235 uranium has 92 protons. So when uranium-235 absorbs a neutron, so a neutron is 1, 0, and N, right? There are no protons. And it splits into zirconium-94. Okay, this one, it actually took me a while to find zirconium on the periodic table. It has an atomic number of 40, so that is zirconium. It splits into zirconium-94, tellurium-139, and tellurium has an atomic number of 52. And additional neutrons, okay? But we don't know how many neutrons. Now, you guys have been balancing these reactions in previous lessons, so that is exactly what we're going to do here. So we just need to make sure our mass and our atomic numbers are balanced here. So if we look at our atomic numbers going in, I have 92 and 0, and going out I have 40 and 52. So those are balanced. Okay? Mass number going in, I have 235 and 1, so 236. And I also have 94 and 139. So 94 plus 139 equals 233. So for this to be balanced, I need to have 3 neutrons. Right? So 3 times 1 is 3, plus 139 plus 94 equals 236. Okay? So this is our reaction. And we are to calculate the energy released during this reaction. Okay? So, we're asked to find the change in energy. But first, to find the change in energy, we need to find the change in mass in the reaction. Okay, and to do that, we're going to subtract the mass of the products from the mass of the reactants. So delta M is equal to mass of the reactants minus the mass of the products. Okay, so let's find the mass of the reactants. So using the table on page 881 in your text, or in that document that I included, you would use that to find the mass of uranium. So the mass of uranium is 235.043930 atomic mass units, plus the mass of the neutron, which is 1.008665 U, minus the mass of the product. I'm just going to move down here. So the mass of zirconium 94 is 93.906315 atomic mass units, plus the mass of tellurium 139, which is 138.934700 atomic mass units, plus 3 neutrons we have. Okay, so we put these into our calculator, and we should get a change in mass equal to 0.185585 atomic mass units. Now let's convert that to kilograms. And that gives us a change in mass of 3.0807. Okay, so we have just found that going from the reactants to the products, we lose 3.08 times 10 to the negative 28 kilograms. Now let's multiply that by the speed of light. Okay, so my change in mass is 3.08, 0711 times 10 negative 28 kilograms, multiplied by 3 times 10 to the 8 meters per second squared. And if you punch that into your calculator, we'll get a change in energy equal to 2.77 times 10 to the negative 11 joules. Or if you want to put this into electron volts, you would divide this by 1.6 times 10 to the negative 19, which is equal to 1.73 times 10 to the 8 electron volts. Okay, so the big takeaway from this example, when we are finding the change in mass in a reaction, it is the mass of the reactants subtract the mass of the products. Okay? Now, one other thing that I wanted to talk about here, now because we have a proton on this side and we have 3 protons there, if you wanted to save yourself a little bit of time, you could just cancel that out, and then this would just become 2 protons, right? So I'm going to do that on the next couple examples, but I just wanted to go through one, not simplifying before I calculate, okay? So in the next couple examples, when I leave out the neutron on the reactant side, it is because I have taken one out of the product side. Okay? So, example 2. So, write the nuclear equation and calculate the energy released when uranium-235 absorbs a neutron and splits into bromine-87. lanthanum 146, and additional neutrons. So we don't know how many yet. Okay, so same thing, we got to make sure our atomic and mass numbers are balanced. So going in, we have 236 for our mass number, and going out, 87 plus 146 is 233. So that tells me that I need to have 3 neutrons to make sure that is balanced. The mass number anyways, okay? And then for our atomic number, we have 92 going in, 35 plus 57 is indeed 92. So we're happy there. Okay, if we're trying to find the energy released, first we need to find the change in mass. Okay, so change in mass is equal to mass of the reactants minus the mass of the products. Okay, and again, you can get your values from that page 881 in your textbook. Okay, so change in mass is equal to mass of the reactants. So mass of uranium-235 is 235.043930 atomic mass units. Now, just like I mentioned on the last slide, I'm not going to add this neutron here, but I'm going to take that away from the product side, okay? So that's going to subtract the mass of bromine 87 is 86.920711 atomic mass units, plus the mass of lanthanum 146, which is 145.92571 atomic mass units, plus 2 times the mass of a neutron. Okay, and again, I only have 2 here because I simplified and took out that 1 neutron from the reactant side. Okay, so punch this into your calculator. You should get a change in mass equaling 0.180098 atomic mass units, which in kilograms is 2.99 times 10 to the negative 28. Okay, so to find our change in energy is equal to change in mass times the speed of light squared. So we'll just substitute in our mass there. Multiplied by c squared will give us a change in energy equaling 2.69 times 10 to the negative 11 joules, which in electron volts is 1.68 times 10 to the 8 electron volts. All right. So again, change in mass is mass of the reactants minus the mass of the products, okay? In this case, it's not final minus initial, like we've been doing throughout the semester, but it is going to be mass of the reactants minus the mass of the products, because we want to find how much of that mass is going to be converted into energy. Okay, so this question here is a little bit different, so don't try to solve it with E is equal to mc squared. Okay, because in this case we know the energy to mass content of our fuel, right? So if a car requires 1600 megajoules of energy to travel 500 kilometers, we're asked how many kilograms of gasoline would be consumed, assuming chemical energy content of the gasoline of 4.4 times 10 to the 7 joules, per kilogram burned. Okay? So for every kilogram burned of gasoline, you get 4.4 times 10 to the 7 joules. Now, we are given a value, so we know that a car requires 1600 megajoules, which if we convert that to joules, it is 1.6 times 10 to the 9 joules. Okay? So to travel 500 kilometers, we need 1.6 times 10 to the 9 joules. Okay? We know that we can get 4.4 times 10 to the 7 joules per 1 kilogram used. So to find the mass of gasoline that we would use, so we just want to, so mass is equal to energy required divided by the energy to mass content of gas or whatever we're looking at in these next two examples, okay? So in this case, energy required is 1.6 times 10 to the 9 joules. And the energy to mass content is 4.4 times 10 to the 7 joules per kilogram. Okay, our joules will cancel and we'll be left in units of kilograms. So we know that we need 36.36 repeating kilograms of gas to allow us to travel a distance which requires 1600 megajoules of energy. Okay? So mass would be 36 kilograms of gas. Now, if you're saying, Mr. Jones, why are we using E is equal to MC squared here? Well, for gasoline, when we are burning gasoline for fuel, we're not disrupting the atomic structure of gasoline. We're just like breaking the bonds of the gasoline molecule, okay? So we're not really doing a nuclear reaction when we're burning gasoline, but we're more so breaking the bonds within that, okay? Now for this next example, where we actually do have like a nuclear example here, again, we don't want to use E is equal to MC squared here because we know our energy content and or energy mass content. So we want to just find out the mass of which we are burning, or how much mass we do need to burn to satisfy that energy distance, I suppose. Okay? So for the second one, so we're asked what is the mass? Okay, how many milligrams of uranium-235 would be required and this is, if we are assuming that we are going through the same amount of energy required, okay? So we're still using, so our energy required here is still going to be 1.6 times 10 to the 9 joules, okay? Because the purpose of this example is to identify how little nuclear fuel we actually need to acquire the same amount of energy if we were comparing it to like a gasoline burning car, okay? So energy to mass content is 7.09 times 10 to the 13 joules per kilogram. So we can use the same formula as we did up top. So mass is equal to 1.6, so our energy content or energy required is 1.6 times 10 to the 9 joules. divided by the energy to mass content ratio, which is 7.09 times 10 to the 13 joules per kilogram. Okay, that will leave us in units of kilogram, which is 2.26 times 10 to the negative 5 kilogram. And if we want to go from kilogram to milligram, we have 6 orders of magnitude. So this becomes 22.6 milligrams. Okay, so 8 orders of magnitude less fuel to get the same energy content, right? So these two examples are just to show the large difference between burning nuclear fuel by changing atoms at the nuclear level, or just by breaking apart bonds within a molecule. Okay? So let's move on to nuclear fusion. So nuclear fusion is kind of the opposite of fission. This is where we have 2 low mass nuclei come together to form a single nucleus with a higher mass. Okay? Mass is still going to be lost. Mass is lost by the nucleons. Okay, in nuclear fission, mass is lost by the nucleus. Okay, so mass is lost by the nucleons, and an amount of energy which is larger than the energy which is produced from fusion is produced. So fusion creates more energy than fission. Okay, fusion, however, requires high temperatures and a strong magnetic field, so that nuclei do not repel, right? If you try to push like the 2 north poles of a magnet together, right, it's going to repel. Similarly, if you try to put 2 nuclei together, they're going to repel one another. Okay, so to get over that interaction or the repulsion between nuclei, we need high temperatures and a strong magnetic field to produce those conditions which would allow for fusion. Okay, nuclear fusion reactions are written similarly to those written for other nuclear reactions, but fusion reactions will have energy as a product of mass loss. And remember, mass is lost by the nucleons. Okay? So, again, when we are doing these reactions, we need to make sure that our mass and atomic numbers are balanced. So this first one here, which is done for you, we have 2 hydrogen atoms coming together to make a helium nucleus, helium-3 isotope, and also a neutron is produced there. Okay? So I would encourage you to try these on your own to fill in the blanks. So on this one, for B, if we have 5 as my mass number going out, right? 4 plus 1 is 5. Then this one must be a 3 for that to be conserved. Okay? Now we need to balance our atomic number. So going out we have 2, and we only have 1 going in, so this must be 1. And if it has only 1 proton, it must be hydrogen. Okay, so hydrogen 3 is tritium, I believe. That's part of heavy water. We'll talk about that in a second. Okay? If it is like this, I do believe it is deuterium. Yeah. Okay, good. Okay, so let's go ahead and predict the products on C and D. So for C, going in, I have a mass number of 4 and an atomic number of 3. So I know that my mass... Okay, the recording just paused there, so I'm not too sure what cut off. But I was just saying that let's make sure that our atomic and our mass numbers are always going to be balanced, right? So C was beryllium 4, right? Because I had 4 mass number going in, so I need to have 4 mass number going out. And I have 3 atomic number going in. 4 minus 1 is 3. So we're happy there. Okay, so for this last one, so we have hydrogen and hydrogen coming together to form hydrogen 3. Okay, and now I'm thinking that hydrogen 3 is actually deuterium. Because hydrogen 2 would be 1 proton and 1 neutron. Let me double check that. Okay? But anyways, we'll talk about that in a minute. That doesn't really matter for now. So anyways, we have hydrogen 2 and hydrogen 2 coming together to form hydrogen 3. So going in, we have 4 as my mass number. So we got to make sure we have a mass number of 4 going out. So that has to be 1. And going out, we have an atomic number of 2. So this must mean that. Okay, so this is normal hydrogen. Okay, yeah. So this is normal hydrogen. When it is hydrogen 2, this is deuterium. And hydrogen 3 is going to be tritium, I believe. And yeah, hydrogen 3 is called tritium. Okay, so hydrogen 2, deuterium, it has a mass number of 2, right? Tritium has a mass number of 3, like a tricycle, and normal hydrogen has a mass number of 1. So just hydrogen 1. Okay. Yeah, so fusion, we're going to have energy as a product of mass loss from our nucleons. Okay, so our sun is a G star, remember? And solar energy is the result of nuclear fusion. And scientists are currently working on making fusion a feasible method for producing energy on Earth. Although radiation is released during the fusion process, it does not have spent fuel that remains radioactive. That is one limitation to fission reactors, is the amount of nuclear waste that is generated as a byproduct. So fusion is beneficial for 2 reasons. 1, it produces more energy per reaction than fission. And 2, it doesn't have like the nuclear waste associated with fission reactors. Okay, so nuclear fusion. This is what we've looked at previously. So here we have deuterium and tritium. So deuterium would be hydrogen 2, and tritium is going to be hydrogen 3. And that is going to form a helium nucleus, a neutron, and it is also going to release energy. Okay, in a nuclear reactor, or a nuclear fusion, or a thermonuclear reactor, yeah, so we have a really hot plasma. We have a strong magnetic field. Remember, we need high temperature and strong magnetic field to, I guess, encourage the nuclei to come together and fuse into a new nucleus. Okay, the heat that is generated during nuclear fusion is going to heat up some water. Water, when it heats up, will turn into steam, which will rotate a turbine, which then creates electrical energy, which will then go out to the grid, right? A little bit of a review there. Okay, in nuclear reactors, a little bit more about this. So heavy water. This is where the hydrogen component is deuterium. So water is H2O. Sometimes you will see heavy water as deuterium H2O. And yeah, so this is where the water or the hydrogen component in water is deuterium, which contains an extra neutron. And this is used as a moderator to slow down neutrons. And this will allow them to kind of interact with uranium-235, and this will result in a fission reaction. Okay, remember, fission is when we have a number with a large mass number. A large atomic number. So we have A is greater than 120. We will have fission. So uranium-235 will undergo fission indeed. And sorry, I just realized earlier I may have said A as my atomic number, but A is going to be my mass number. Okay, so when my mass number is greater than 120, right? Because so uranium only has an atomic number of 92, which we use as Z, right? So A is the mass number, which is 235. So it has a mass number greater than 120, like uranium does. It will undergo fission. So within nuclear reactors, so control rods, which are typically made of cadmium, these are used to slow down fission by the absorption of excess neutrons. Now, as what we found in the case of Chernobyl, these control rods were not able to be, they were not able to slow down the fission. They weren't able to insert the control rods, so the nuclear reactants eventually became out of control. Too much heat was being produced, and then we had that big explosion. Okay, so on a normal working nuclear reactor, when the reactor vessel is increasing in temperature, the control rods will be entered. This will to absorb excess neutrons and to slow down the rate of fission so that we do not have overheating and so we don't have a meltdown. Okay, fission of uranium occurs in a containment building where the moderator also acts as a coolant and takes the heat energy away. So the water is kept under pressure so that it will not boil. And the energy of the heavy water is then passed to water in a separate container. So if we jump back to this slide here. Okay, so if you're going to have your water in here, right, containing the heavy water of deuterium, this is under high pressure. Okay, and as we increase the pressure, we are also going to increase the boiling point, because if there is more air pressure, the fluid itself is going to need to have more energy to compensate and to get over that high air pressure. Okay, and same kind of thing, if you're like trying to boil or cook potatoes on a mountain, because there is less air and therefore less air pressure in the mountains, water is going to boil at a lower temperature. And if you're trying to cook potatoes, you will be disappointed because your water is actually going to be boiling at, I don't know the exact temperature, but it's not going to be boiling at 100 degrees Celsius. Okay? So, the water is kept under pressure in that one containment like I just talked about in here. Okay, that water is kept under high pressure so that it does not boil. And then the energy of the heavy water is passed to water in a separate container. And this is where the water will boil and generate steam, like we saw in this image, right? So the heat is transferred to the actual heating containment unit, and that is what's going to generate the steam to rotate the turbine. Okay, steam will drive a turbine to generate electricity, and then waste heat is going to be discharged into the air or in a body of water. That's why typically nuclear power plants...
Willie to the office, please. Willie to the office, please.
That's why typically nuclear power plants are found near bodies of water. Okay, and this is just kind of an image here of what we just talked about. So this is the reactor where we have the heavy water under high pressure. So it does not evaporate. Okay, that energy is transferred into the steam generator, which will warm up that water, create steam, which will rotate a turbine. As the water cools down, it will either enter a cooling tower or they will emit that warm water into the atmosphere or into a body of water. Okay, so that is it for chapter 16. So for the remainder of today's class, I want you to watch all those lessons or the videos that I mentioned in this lesson. And then you guys are going to work on a chapter 16 take-home quiz. Okay, so instead of doing practice problems for this topic, I'm just going to give you your take-home quiz. Okay, so if you have any questions about today's lesson or anything else in this course, please don't hesitate to reach out. I'd be happy to answer them for you. Okay, thank you and have a great day. We'll see you soon.